Yeah, hi, I'm back again. So in the part 2 and part 1, we mainly talk about how to use Merlin to train the parametric speech senses. So in the last part, I will talk about can we do something different if you already know how to use Merlin to do parametric senses. In the extension part, I will talk about the 3 topics. The first one is for hybrid speech senses. I think many people are interested in hybrid speech senses. It's very popular in industry to get a high quality speech. The second topic will be voice conversion, how to modify one speaker's voice to sound like the target speaker. The third topic will be speaker adaptation, how to create a new voice with a small amount of data. So let's start on the hybrid speech senses. Hybrid speech senses is still a unit selection, so I will talk about what's the basic idea of unit selection. Let's start with an example how to synthesize Simon. Here I mean not to clone a new Simon. Here is to create the speech to pronounce Simon. We have some candidate unit. We need to find a sequence of unit to make the sound. For example, we can get one pass.
Simon.
Yeah, we can get a sequence of unit to make the pronunciation. We can get another pass.
Simon.
A different pass, the pronunciation may be slightly, the quality might be slightly different. We can get another one.
Simon.
You can see this one is slightly better, but you can still hear some very obvious issues, for some glitch in the synthesized audio. This is because in unit selection, we have 2 important factors, target cost and joint cost. The target cost means we give a reference target, we compute the cost between the reference and the candidate of the unit. Usually, in the classic unit selection, we use some category features to compute the target cost. The target cost is a kind of to make sure the synthesized voice has a good intelligibility and also have a good prosody. So we also need a joint cost. Joint cost is to make sure the synthesized voice is smooth, to make sure there is no very obvious glitches. So usually we use some energy features, some acoustic features to compute the joint cost. There are several ways to implement the target cost. For example, use Paul Tyler's terminology, the first one we call it independent feature formulation. Here means for the target reference, we give some category features. For example, the phoneme content information, like Srikan already present. Also some stress information from the front end, and some positional features, like Srikan already present. That's using independent feature formulation. We can also use the acoustic feature formulation. In the acoustic feature formulation, the reference target is some acoustic features. So we compute the distance between the reference acoustic feature and the acoustic feature of the candidate. So we can get some value for the target. So for the hybrid speech senses is like unit selection with the acoustic speech formulation. Here, if we want to generate a waveform, we first predict a sequence of acoustic feature as a reference for the target cost, and then we compute the target cost based on the acoustic feature and the candidate. Because here we are not going to use the acoustic feature to generate a waveform directly, so the feature for the reference can be any features. Some feature even may not be able to synthesize voice. I think from another point of view, hybrid speech senses is also like parametric senses. Here we use the unit selection to replace the vocoder. in parametric synthesis, after we predict the acoustic feature, we use a vocoder to generate a waveform. But here in hybrid synthesis, after we get the acoustic feature, we go through the database, do the concatenations, and then generate the waveform. So here, we don't use a vocoder, so we can use any feature as you like to predict the reference. In last 2 years ago, we have a paper. We use a bottleneck feature rendered from the neural network. Use the bottleneck feature as a reference target. To learn the bottleneck feature, the input is a linguistic feature. The output is an acoustic feature. Actually, this is exactly the same as we talked in part 2, but only in the network we have a bottleneck layer. The bottleneck layer is a low-dimensional representation of the features. Of course, we can also predict the distribution to compute the target cost and the concatenation cost. If we predict the distribution, we can compute a kind of likelihood value as a target cost. I'm not going to go to detail here. If you are interested, you can go to our post on Thursday morning. You can, if you want to take a photo for the paper, please go ahead. Let me play you some samples to build hybrid synthesis using Merlin and Festival. Festival, as Simon already mentioned, is provide the front end and also do unit selection. So we can combine Merlin prediction with Festival to do the hybrid. The Festival unit selection is a benchmark baseline system in the last year Blizzard challenge. The second system is the CSTR entry we submitted last year. We got quite good results. First example.
Meanwhile, Fogg's friends at his club had spent the last few days in a fever of excitement.
Yeah, you can hear some glitches here.
Meanwhile, Fogg's friends at his club had spent the last few days in a fever of excitement. He collected as many as he could and stuffed them into his pockets. He collected as many as he could and stuffed them into his pockets.
Yeah, if you want to build a system, I think you can try to check the speedrun website. I think there will be a web post from CSTR to show you how to do the implementation to combine the Merlin system and the Festival to do the hybrid. It's coming soon. So that's about the hybrid speed synthesis. So the next topic is I'm going to talk about is the voice conversion. How can we change Merlin toolkit to do voice conversion? Voice conversion, I think is from the name, is very easy to understand. Is to manipulate the source speaker's voice to sound like the target speaker without changing the language content. For example, I can speak one voice, one utterance, and through the voice conversion to sound like Simon. So basically, it's a mapping problem. So we can use a neural network to do voice conversion. The input will be the source speed signal. The output will be the target speed signal. So the difference between voice conversion and the parametric synthesis we talk about in part 2 is only the input data. The input data here is the speed signal, not the linguistic features. So we still need some solutions for the acoustic feature engineering and also align the input and output features. So give a sequence of the input waveform. We need to get some feature representations for the neural network input. But here we are not going to generate speech directly from the input feature. So actually the input feature can be any feature you like. For the output waveform, for the output feature, because we want to synthesize voice, we want people to listen to the synthesized voice, we need some vocoder features to generate the acoustic feature for the neural network output. For the two different speakers, when they speak the same language content, their duration may be different, their processing may be different. So to make sure the language content is not changed during voice conversion, we need to do an alignment between the source feature and the target feature. The purpose is just to make sure the language content will not be changed. The language content is aligned. So here is a diagram how to do voice conversion. This is a very simple approach to do frame by frame using a feed-forward neural network. The input is the acoustic feature. The output is a corresponding aligned output feature. So during training, we can do the frame by frame regression. At the runtime, give one frame as the input. We just predict the corresponding one frame output. This is do frame by frame. We do not consider the context information. Speech is has many temporal information, so it's better to use some sequence model to do the regression. Here in the LSTM is still using the aligned input and output features, but it will consider the contextual information. This paper is published by Lifa, but you can also easily do it with Merlin. We already provide some examples in the GitHub, in the Merlin system. You can go to the example, the voice conversion directory. There are 6 steps. You can follow these steps to build your voice conversion system. It can give you a reasonable quality speech. Because the only difference between parametric synthesis and voice conversion is the input. So the alignment is also different from parametric synthesis. So in the repo, we also provide some script to align the source and the target features. Is a very classical dynamic programming alignment. Here I want to play you some samples we made using the Merlin toolkit. The first example will be the source speaker.
Author of The Danger Trail, Philip Steele, etc.
It's a male voice. The second is the target speaker.
Author of The Danger Trail, Philip Steele, etc.
It's a female voice.
Author of The Danger Trail, Philip Steele, etc.
Yeah, you can see the converted voice is very close to the target. It can give a very reasonable speech. So the last topic will be speaker adaptation. I think recently is also a very hot topic. So in speaker adaptation, the purpose we want to do adaptation is we want to create a new voice with a small amount of data. For example, usually to build a TTS system, we need several hours speech. But speaker adaptation maybe only requires a few minutes or even a few seconds speech to create a new voice. To do that, usually we train an average voice first using hundreds of speakers. After that, given a few minutes speech from the target speaker, we can easily do an adaptation to match the target speaker's feature distribution. In the neural network framework, we have different ways to do the adaptation. I think the first one, very easy way to do that is we can append the I vector as an input to the neural network to do the adaptation. I vector is a very popular technique used in speaker recognition. It's a low-dimensional feature representation to represent the speaker identity. Of course, we can put some gender code or even some accent code. The second very easy approach is we can do a feature mapping at the output. This is very similar to voice conversion, just a feature mapping problem. If you do not want to change your neural network, you can simply train a mapping. The third way is we can do some modification to the models, to the model parameters. We had a paper 2 years ago. We tried to learn the hidden unit contribution to do a scaling of the hidden activations to match the target speaker's feature distribution. I'm not going to go to detail for this technique. You can read our paper published in Interspeech 2015. Another technique proposed by Microsoft, they use the head swapping. So in these techniques, all the hidden layers are shared by all the speakers. Only the output layer is speaker specific. So actually this technique is very similar to apply a transformation at the output. Yeah, of course, if you have enough data, you can retrain the model. But I did not see any paper did that. I will play you some samples. This sample is from our paper 2 years ago at the Interspeech Dresden. The first is a target speech.
The knife was hung inside its bright sheath. The knife was hung inside its bright sheath. The knife was hung inside its bright sheath. The knife was hung inside its bright sheath.
Others have tried to explain the phenomenon physically.
Others have tried to explain the phenomenon physically.
Others have tried to explain the phenomenon physically. Others have tried to explain the phenomenon physically.
Yeah, for this example, for the different adaptation techniques, they apply the adaptation at the different levels of the neural network. Actually, you can easily combine the three methods into one framework. I'm not going to show you examples. You can go to our webpage to download the examples.